today to SPI lectures. My name is Negedu Godwin and I'm your regular anchor. I want to show my sincere appreciation to these wonderful people who have contributed greatly to my knowledge. Today we're going to be dealing with sound and sound wave parameters. So what is a sound wave? Now, we already know that sound is a mechanical process that is caused by a vibrating source. An example of such vibrating source is a vocal cord or a guitar. Sound is a type of mechanical pressure wave that travels longitudinally in air. And the frequency of a sound wave is the number of vibrations that occur in 1 second. Categories of sound frequencies. We have the audible sound audible range. Sound frequencies that falls within a range that can be heard by humans are audible frequencies. Now, this range of frequencies will extend from 20 vibrations per second to 20,000 vibrations per second. In music, the frequency of sound is actually what they call the pitch of the sound. While infrasound, sound frequencies below the range of human hearing, and these are below 20 hertz. Now, we cannot hear these low frequency infrasound, but we can often feel the vibration. And you note that many modern stereo systems contain these subwoofers, which generate low frequency sound that adds this visual feeling to the listening experience. But ultrasound is sound frequencies that are above human audible range. And these frequencies are anything from above 20,000 hertz or 20 kilohertz. Ultrasound also cannot be detected by humans, but can be sensed by certain animals such as dogs, bats, and so on. Now, what are the medical uses of ultrasound? At this point, we'll take a break and I will be right back.
Welcome to the best online ultrasound training channel in Africa. Looking to advance your skills in ultrasound imaging? Look no further than our online ultrasound training lectures. Our comprehensive courses covers a wide range of topics, from the basics of ultrasound technology to advanced techniques and applications in obs and gynae, abdomen and pelvis, echo, small parts and vascular ultrasound. With expert instructors and hands-on training exercises, you'll gain the knowledge and the confidence you need to take your ultrasound skills to the next level. Whether you're a healthcare professional looking to enhance your expertise, or a student pursuing a career in diagnostic imaging, our online ultrasound training lectures offer a flexible and convenient way to learn. You can access our course anytime, anywhere, and at your own pace on YouTube, Ambernet channel, or visit our online store at ambernet.business.site, or send us an email at sonoeyesdiagnostics@gmail.com. You can also WhatsApp +234 9019 144 175. Don't miss this opportunity to expand your ultrasound knowledge and advance your career. Enroll in our online ultrasound training lectures today and start your journey towards success. Sono Eyes Global Health Services, building diagnostic capacity in Africa.
Welcome back. Let's look at the medical uses of ultrasound. Here you see the spectrum of medical ultrasound. There you have the ultrasound range, the audible sound range, infrasound range. You have the sound range, ultrasound range for ophthalmology, for pelvic, for abdominal, obs and cardiology, and also that necessary for therapy. Diagnostic medical ultrasound uses the range of very high level frequencies that is required in medical imaging, and these frequencies range from 2 megahertz to 12 megahertz. But however, the upper limit of the range is being pushed all the time with advent of very high frequency that is used in the endoluminal probes. Now, these probes may have frequency as high as 30 megahertz with a penetration ability of 0.5 centimeter to 2 centimeter. Now, the choice of frequency is a trade-off. You want to choose which frequency to use. It's a trade-off between the image quality and the image depth, the penetration. So you want to consider how deep you want to go and how much quality can you get in that depth, vis-a-vis, vice versa, I mean. So higher frequency probes will produce higher resolution image but less depth. So lower frequency probes will produce less resolution or poor quality image but deeper penetration. There are measurable quantities that vary within a medium as sound is propagated through a medium. Now we need to know the 4 acoustic variables that affects the propagation of sound, and that will include pressure, density, particle motion, and temperature. With respect to pressure, this is the amount of force in a given mass, and it is measured in Pascal, pounds per square inch, and Newton per square meter. Density is the mass per unit volume, and the units are kilogram per meter cube, gram per centimeter cube, or pounds per feet cube. Particle motion is actually the distance moved by the molecules in a medium. The unit is a unit of distance, which is typically in nanometer. A sound can be described by the following parameters. You can describe sound in frequency. You can describe sound in power. You can describe sound in velocity, that is propagation speed. In frequency, parameters involved are period and wavelength. In power, parameters involved are intensity and amplitude. Frequency is the number of times per second the piezoelectric crystal will vibrate. In other words, expand and contract to produce waves. So in clinical practice, the effective transducer frequency range is governed by the depth, size, attenuation coefficient of that area of interest. And this table gives us the frequency equation and the description of those parameters. There are factors that limit the choice of transducer frequency. So the choice of a transducer frequency is used in the diagnostic ultrasound is limited by 2 factors. The first is tissue penetration, that is the image depth. The second is the spatial resolution or the image quality. The higher the frequency, the better the spatial resolution. But penetration into the deeper tissues will be limited. Relationship of frequency with depth. What's the relationship of frequency with penetration? Depth or penetration, I'll use them interchangeably, is inversely related to frequency. Now, if the frequency increases, the depth of penetration decreases and vice versa. And if the frequency decreases, the penetration depth increases. In soft tissue, the relationship is linear. Doubling the frequency will result in half the penetration. The relationship of frequency with image quality, that's axial resolution. Here you have the image quality is directly proportional to the frequency. Now, if the frequency increases, axial resolution improves. But higher the frequency, the better the image quality. So why does penetration decreases with increased frequency? It's all due to attenuation. And attenuation means the gradual weakening of the strength of the sound wave or the echo returning. It is defined as the gradual reduction in the amplitude and intensity of the incident wave as it travels through the tissue. Attenuation occurs through three processes. Attenuation occurs through absorption. 80% of the sound wave is absorbed. Attenuation occurs through reflection and through refraction or scattering. Now, I want you to take note of these things, of these important points. As attenuation in a structure increases, the depth of penetration decreases correspondingly, yeah? So as frequency increases, so does the attenuation increase. So as a rule of thumb, use the highest frequency that will penetrate the depth of interest. So this is a typical scanning frequency range in diagnostic ultrasound. For general abdomen, we use 2 to 5 megahertz. To image the gallbladder, we use about 3 to 5 megahertz. For OBS and gynae, you can use 3 to 7.5 megahertz. Thyroid, breast, and scrotum, you can use 5 megahertz to 12 megahertz. Adult heart, you use 2 to 3 megahertz. Pediatric heart, you use 3 to 5 megahertz. For eye ophthalmology scanning, you can use 7 to 15 megahertz, while endoluminal ultrasounds will utilize 15 to 30 megahertz. As one of the variables we are discussing with respect to frequency, we look at period. And period is the time it takes for a sound wave to complete one single cycle. The equation of period is period in microseconds is equal to 1 over frequency in megahertz. The unit of period can be measured in seconds, milliseconds, or microseconds. For example, at 5 megahertz, the period is 0.2 microseconds. Clinically, the frequency of a sound wave is very important, but the period is not, clinically speaking. However, period is useful to understand the pulse ultrasound and biological effect, which we'll deal with in other classes. Wavelength, another variable, is the distance a wave has to travel to complete a single cycle, and is measured in meter, centimeter, or millimeter. Wavelength depends on two factors: the speed or velocity of the wave and the frequency of the wave. If either of these parameter changes, the wavelength will change. The relationship is known as the wave equation, and the wave equation is velocity is equal to frequency lambda, or as you have it in these equations. So what is the clinical significance of wavelength? The sonologist rarely thinks directly about wavelength while operating the ultrasound system. He thinks about transducer frequency and also about focus, basically. However, each time the transducer is changed, the wavelength by necessity will also change. Wavelength affects the pulse length, which is a direct measure of axial resolution. Therefore, from a clinical perspective, shorter wavelength means shorter pulse length, shorter spatial pulse length. Shorter the pulse length, higher the axial resolution, thus better image quality. Velocity of propagation of speed of sound is actually the rate at which sound waves travel through medium. The speed or velocity of sound through a medium is determined by physical characteristics of that medium through which it's being transmitted, and is not determined by frequency or the wavelength. It's just the physical characteristics of that medium. Speed of sound is determined strictly by the medium. Don't forget that. Now, this means that different media propagate sound at different speed. Now, this table shows us the velocity of sound in soft tissue, air, and other body tissue. For example, air, the velocity of sound in air is 330 meters per second. That of lungs is 600 meters per second. Fat is 1,460 meters per second. You can see velocity of sound in water at 50 degrees is 1,540 meters per second. Also the same for soft tissue. Then you see propagation of sound in muscle is 1,600, and that of bone is 4,080 meters per second. Now, two physical characteristics of the medium which will determine the velocity of sound are stiffness and density. And stiffness actually will mean the resistance to compressibility. So the velocity of sound is directly proportional to the stiffness of the medium and inversely proportional to the media density. And the equation is velocity of sound, the stiffness over density, and the whole parameters are stated clearly for you to see. We can express these relationships slightly differently by using the term compressibility or elasticity rather than stiffness. However, since both compressibility and elasticity are opposites of stiffness, the relationship can be expressed as velocity of sound, which is inverse to density times compressibility, or velocity of sound is inverse to density times elasticity. The stiffness of a medium is due to the strength of its intermolecular bonding. If the molecules are tightly bound to each other as they are in a solid, then the media or the medium is stiff and the propagation of sound through the medium is high. But on the other hand, if the intermolecular bonding is weak, as you will find in gas, then the propagational speed of sound through the medium will be slow. In density, this is the mass of the medium per volume, right? So the denser the media, the slower the propagation. This makes it much more difficult to get the molecules moving because it's denser and the sound wave propagates very slowly. So it is also a trade-off between stiffness and density. The stiffer the medium, the higher the propagation speed. The denser the medium, the lower the propagation speed. Now, it is the stiffness of solid material like bone that gives much higher propagation speed. What about the speed of sound in soft tissue? Because we're talking about diagnostic ultrasound. So the difference in density and stiffness between soft tissue organs of the body, like you have liver, spleen, kidneys, are very small. So the velocity of sound in human soft tissue is generally considered to be a constant of 1,540 meter per second or 1.54 millimeter per microsecond. Please take note of the conversion. It can be tricky. So this value is very important because it is the calibration value that is used by ultrasound system to calculate the distance on the display. So all ultrasound machine assumes the velocity of sound is constant, which allows the instrument to generate image. Well, that assumption also will result to a problem which we will deal with as we go on. Now, range equation. Now, ultrasound imaging instruments operate on pulse echo principle. A pulse of ultrasound is sent into the body from the transducer. Yeah. Now, that pulse travels down into the body at a propagation speed of sound in soft tissue, which is a constant of 1,540 meter per second, or when you convert it, 1.54 millimeter per microsecond. The tissue interface produces echo, which returns to the transducer for processing. On returning to the transducer, the ultrasound system assesses the amplitude of the echo, and using the time between the transmission and the reception, it will calculate the depths of the originating interface. So to calculate the depth of each echo, the ultrasound system will use the range equation, which is distance equals to speed times time divided by 2. Or you may also find it written as reflector distance in millimeter equals to 1.5 millimeter per microsecond times go return time in microseconds divided by 2. Distance is directly proportional to go return time. So deep echoes will have longer go return time. Superficial echoes will have shorter go return time. So let's look at amplitude, power, and intensity and how it interplays to give us ultrasound imaging. The amplitude of a sound wave is the strength of the wave or the peak height of the wave. When we want to express ratio between two amplitudes or two power or two intensities, we use the unit decibels. The amplitude of a sound wave decreases as ultrasound travels in tissue. This loss in amplitude is called attenuation. Increasing the amplitude of the outgoing ultrasound wave will increase the depth of penetration. Now, this allows the system to receive and display echoes from more further distant interfaces. The amplitude of the ultrasound pulse is controlled by the output power control. A higher electrical voltage will cause a transducer crystal to vibrate more strongly, producing a higher amplitude ultrasound pulse. This control button on your machine is commonly labeled as power or output. And in some machines, you may not even find it there because it's automated. Power is the rate at which work is performed, or is the rate at which energy is transferred. It is the rate at which work is performed. And in the case of ultrasound, the work performed is the production of ultrasound wave by the transducer and the propagation of that wave through tissue. Now, the relationship of power with amplitude is this. Power is proportional to amplitude, the squared amplitude. For example, if an amplitude is increased by a factor of 2, then power is increased by a factor of 2 squared. The power is increased by a factor, eventually by a factor of 4. So power is proportional to amplitude squared. Intensity. Intensity is the concentration of power in an area. It is the power in a beam divided by the beam's cross-sectional area. The unit of intensity is watt per centimeter square or milliwatt per centimeter square. In diagnostic ultrasound, ultrasound intensity typically will range from 0.1 milliwatt per centimeter square to 100 watt per centimeter square. And intensity is equal to power over area. Power is proportional to intensity. Power is also proportional to the amplitude squared. Intensity is proportional to the squared amplitude. So there is an inverse relation between beam area and intensity. Now, if area decreases, intensity increases. For a given power level, intensity is greatest where the beam area is smallest. The region is called the focal point. That region is called the focal point. So ultrasound beam intensity is highest at the focal zone. Now this understanding is important so that you avoid biological effects in body tissues. Now I want to introduce us to bioeffect, power and intensity. And bioeffect we will discuss more on in the process of time. So power output of a transducer is an operator selectable control on most ultrasound machines. I've said that before. So that means you can adjust it. The minimum output power needed to obtain an adequate image should be used because of our concern for potential adverse biological effect. So using the lowest available power setting on the machine, if you use the lowest available power setting on the machine, you minimize the ultrasound dose that is delivered to the patient. There is no solid proof yet that any damage can occur with energy output of diagnostic ultrasound system, but we have to be very prudent and cautious in our attitude to avoid any biological effects. So the beam area at any distance from the transducer's face will depend on the crystal diameter, sound frequency, and focusing. The beam is the most intense, that is to say the highest intensity in the focal zone of a transducer, because this is where the beam or the diameter is smallest. This is also the area where the best lateral resolution of the transducer is found. Here, let's assume acoustic power for 2 transducer is 50 milliwatts. Yeah, for transistor A and transistor B. Transistor A has an area of 2 centimeters square, while transistor B has 8 centimeters square. The intensity for transistor A, of course, we know that is power divided by area. So what's the power? 50 MW divided by 2, which is the area, which will give us 25 milliwatts over centimeter square. Then for transistor B, it will be 50 divided by 8, which we have 6.2 milliwatts over centimeter square. So transistor A has a tightly focused beam than transistor B. The beam area for transistor A is 2 centimeters square, giving the beam intensity at the focal point of 25 milliwatts per centimeter square. And the transistor B has a beam area of 8 centimeters, giving the beam intensity of 6.2. Now, the intensity of an ultrasound beam is an important, and I keep stressing, is an important consideration in biological effect on tissue. And that's the reason why we should know about the intensity of ultrasound beam. Experiments have found that the biological effects of ultrasound are directly related to intensity and the duration of exposure. Intensity can be measured in 6 different ways as follows. You can measure intensity in this table is well explained in spatial peak intensity. And spatial peak intensity is the highest intensity at the focal point of the beam. You have the spatial average intensity, which is the average intensity at the face of the transducer. We have the temporal peak intensity, and that is the highest intensity of pulse when sound is on only. Temporal average intensity is the intensity average over time when sound is on and off. Pulse average is the intensity average over the duration of pulse on time only, while maximum intensity is the intensity average over the largest half cycle of the pulse. There are 4 parameters used in combination for intensity. You have the SATA. So I want you to use this table and go back to the previous table. The combination of those parameters gives us these 4 combinable parameters for intensity. So SATA is the average value of intensity average over on and off time. It is the lowest or the smallest intensity measured along the beam. SATP is the average spatial averaged over on time of the pulse, while SPTA is the intensity of the beam as its maximum point averaged over time, both on the on time and the off time. It is the truest representation of exposure by biological tissues, which we measure to study bioeffects. SPTP is the intensity of the beam at its maximum point averaged on time. It is the highest intensity that is measured along the beam path. But you need to note that in continuous wave ultrasound, the TP and TA values are equal because it provides a continuous transmission of ultrasound energy. There's no off time or pulse time. It's continuous. So here's a summary of the relationship between power, intensity, and amplitude. Power and intensity are directly proportional. That's to say, if power is increased by a factor of 3, intensity is increased by a factor of 3. If power is reduced by a factor of x, the intensity is reduced by a factor of x. Power is proportional to amplitude squared. If power is increased by a factor of 4, power is increased by a factor of 4 squared. If amplitude is reduced by a factor of x, power is reduced by a factor of x squared. Intensity is proportional to amplitude squared. If amplitude is increased by a factor of 5, intensity is increased by a factor of 5 squared. If amplitude is reduced by a factor of x, intensity is reduced by a factor of x squared. And I'll put it there for you to see and know it. Here's the table to summarize the parameters, their basic units, and what can determine those parameters and whether or not the operator, the sonologist, can change. Frequency cannot be changed by the operator. Period cannot be changed by the operator. Wavelength cannot be changed by the operator. Power can be changed by the operator. Intensity can be changed by the operator. Amplitude can be changed by the operator. I want to thank you for joining this lecture. Please like, share, subscribe, put on your notification to receive all our free lectures. For more information about our paid classes, please send an email to sonoeyesdiagnostics@gmail.com, or you can WhatsApp me at +234 9019 144 175, or visit our online store at sonoeyes.business.site or ambaneg.business.site. Attempt the quiz in the description and leave me a comment. Until the next time when I come your way again, keep learning ultrasound.